Todo lo que escribas en estos formatos se va a transmitir.
Si necesitaré eso.
¿Quieres un pincho?
Sí, bueno, puede ser interesante, pero...
Sí, sí.
Yo quité...
Ah, no te lo mires, luego lo haces.
No, pero es que... No, pero necesito conectar el pincho.
Yo creo que solo tienes una USB. El sonido lo está enviando de aquí. Si hablas aquí,
Sí.
mejor. ¿Vale? Bueno, a ver, aquí, remover, pero que sepas de dónde viene. Voy a quitar de aquí. Sí, bueno, espera. Bueno, tienes puesto en tu ordenador.
Sí, bueno.
Claro, el Zoom, al retransmitir por el Zoom, esta pantalla de Zoom, tú estás compartiendo, tú tienes que pinchar fuerte, tienes que pinchar en tu PowerPoint directamente aquí, en tu ordenador, que a lo mejor está pinchado el Zoom.
Sí, voy a ver.
Vale, ok. Aquí, no, ahora mismo no. En Zoom sí se está viendo bien.
¿No se ve?
Sí.
Sí, bueno, pero la norma
En full screen.
tendría que haber entrado las opciones de visualización del Zoom para quitar esa barra y como lo tenía en la otra pantalla, bueno, se ve.
De hecho, puedes recortarla aquí si quieres.
En el OBS sí, por lo contrario, en el OBS está transmitiéndolo.
Vale, quieres dejar la pizarra, por eso. Vale.
Sí, y la pantalla que se te ve como entonces, so we start. I'm going to start in English. Okay, so it's a pleasure to meet and introduce you to González Hernández. He did his thesis in the ASC. After that, he moved to the Barros Observatory, and after that, he moved here to the Complutense, and after that, he came back to the ASC. He is deeply involved in the ESPRESSO consortium, and he's going to present us the latest results from the consortium regarding the detection of a planet along Barnard star. So,
thank you very much. So, just to start, this has been a long process to arrive here. I would like to start with this because it's how we can, just to have an idea of what we are doing at the IAC. This is typically similar to Alliance, and we are doing from solar physics, solar system, stellar physics, galaxies, and then exoplanets as well, and then also going back to the stellar galaxies and also cosmology, all the fields in astronomy. But we are also doing a lot of instrumentation related to research, and we are placing at the GTC, of course, and also at the ELT, and then at the DLT, and also some instruments at the ELT. And my current work at IAC is in between these two branches, between science, general science in different fields, and also I also share my work on instrumentation. To start with, this is just a typical field of star. This is what we see, and this is what we think it is. So indeed, we think right now that all the stars should have planets around. This is a conceptual feature put. But then we also want to compare our solar system with the rest of the systems in the galaxy, and to understand if the solar system is really a system that is seen as a reference system for evaluating the exoplanets and exoplanetary system. This is a typical picture that we put in exoplanet science with mass versus periods. And here you can see the different planets that have been already discovered. We are now around 5,500 exoplanets known. Most of them have been discovered using either the transit method, which is most of them coming from the transit method, and many of them also, almost close to 1,000, have been discovered using the transit method. Here you see typically that the transit method is always picking at short periods because of the missions that have been sent to the typically to space, of course, and the fact that the transit probability is highly dependent on distance from the star. On the contrary, the radial velocity method is distributing the discoveries in a wider range of spectral periods, orbital periods, and it's going to shorter periods as we go to lower masses because of our capability to detect planets. And there is one single object or one class of objects that we call super Earth, and this is especially important because it was discovered at the beginning of the 2000s. And it is a type of planet that is not present in the solar system. Indeed, from the Kepler statistics, one can see that the super Earth and Neptune size, or even Neptune size, the most numerous. In between this peculiar or let's say this kind of exoplanet that we don't see in the solar system, but we see out there, we can see that there is this peculiarity in this range of radius of the planets. If we do 1.5 and 2, we are seeing that there is like a gap or a scarcity of planets. And this is what is called the Fulton gap. And this is driven currently many of the results of the observations in exoplanet science to understand this modality. And there is new works that have been done leading by people at TESS, and IPARCOS, where they are showing that this difference in radius or this gap in radius is different if you instead you plug it in density. And they said that the difference between the sub-Neptunes and the super Earth is not the fact that the planet has or not an envelope, but the fact that the planets have there is this possibility that the planets are changing from the snow line, they are changing from orbital periods that are longer to shorter periods, and this is understood by density. So from the current statistics in exoplanets and the current statistics of the latest papers in the Kepler field, there is this new paper that shows that almost on average every star has a planet. In particular, the statistics go from almost 1 day to 400 days, so it's quite complete, and it's including from 0.5. This is Earth radius, and 16 Earth radius, this is not solar radius. So considering all the planets, on average, every star should have a planet. This is what they said at the beginning of the talk. And in particular, this is very interesting, is that this Eta Earth, which is the planets in the similar to Earth and in the habitable zone, it seems that the statistics show that 10% of the stars has a planet like this. So this is quite general. This is just to show you that the transit method is based on the fact that this planet is just a cool part of the life on the stellar peaks. And that's why this is the way we are detecting the planet, the transit, as I said. The transit probability, if you change a little bit the inclination of the orbit, this is not possible to detect. On the other hand, the radial method doesn't care about the inclination. It's always, we have always the limitation that we need to know the inclination is somehow conditioning our mass, but so we are always measuring the mass, the minimum mass of the planet. But typically what we are seeing in this method is the oscillation, periodic oscillation of the star in the line of sight. And from that, and from the mass of the star, we can get the mass of the planet. So in particular, currently, people in exoplanet science, they are taking care of the solar neighborhood, because this is the stuff that we will be able to study in the near future with current instrumentation that is being developed. In particular, in the solar neighborhood, what we know is that most of the stars are endless. So naturally, it is expected that most of the most of the observations are currently being done around endless to be able to detect planet in this class of stars. So particularly, if we compare the Sun with an endless, we see that the size is smaller, of course, than the mass. And this is in the direction of making it easier to detect planets, and in particular small planets, either for in transits or in radial velocities. Another point is that the stars are cooler than the Sun, so particularly the habitable zone is closer to the stars, so this makes it easier to detect planets in the habitable zone. This is the list of potentially habitable exoplanets by 2023. I don't think this has changed the last year. My team, and this was this was a paper of ESPRESSO, but we also had a collaboration with Hernández in this regard. And these two planets are led by the postdoc working in my group. And there is this Hernández that was one of the most important discoveries of Hernández group. And there is also, of course, Proxima. So from the 80s, the radial velocity method have been evolving quite significantly. In the 80s, we were measuring the radial velocity with a precision of 15 meters per second. That was really dramatically, it was evolving with newer instruments, but then with HARS in 2003, we jumped to the 1 meter per second. This changed the exoplanet science everywhere, and indeed HARS and HARS are currently performing at even below the meter per second. And then with ESPRESSO, we were reaching the 10 centimeters per second, and why 10 centimeters per second? The reason is that it is connected to the fact that the gravitational pull of the Earth on the Sun is 9 centimeters per second. And this was the reason why we were pushing to get this instrument. So this involved significant funds, of course, these developments, significant engineer, human resources, Of course, the observing facilities are also playing a role. Having a bigger telescope helps a lot. And also the improvement of the data analysis is a significant contribution. So we are going here from energy highlights for our parts and then going up to current ESPRESSO. This is qualitative, it's not really, the points are the dots are put there approximately. So from the first exoplanet orbiting a solar type star discovered by Demangeon and Barros in 1995, published in Nature. This was 0.5, so Jupiter mass. So Jupiter-like planet has an amplitude close to 60 meters per second, and the orbital period was 4.2. So like Hot Jupiter orbiting faster, close to a host star. And this was the rarest because there was we could do at that time. And this, in comparison with the detection of Proxima B by colleague in Spain, González, published in 2016, with this amplitude of 1.4 meters per second at the time, period of 11.2, and a mass of 1.3, Earth masses, and this being the closest star to our Sun, which is before this period is within the habitable zone. This was the discovery, I would say the discovery in the solar side have been the highest impact in the last decades. And this, the discovery of the first planet and the fact that they initiated this career, the exoplanet science in this way, gives the Nobel Prize in 2019 to Mr. Maria and the fellows. So I will start with Carmenes. Carmenes is having a very successful project. It's still going on. It's visible near-infrared far-infrared exoplanet, far-infrared spectrograph at the 3.5 meter telescope in Colorado. It is a high-resolution spectrograph. It goes from 500 nanometers to 1,700. And it has been discovered many exoplanets, many of them on many of them small exoplanets, and all of them the project of course it was focused on indoors. This is, I would say, the list of more relevant results from the Carmenes team. I would like to emphasize, apart from the candidate in Barnard, the tea garden to me is the most important result of Carmenes, and also the detection of helium in the atmosphere of an exoplanet is also a significant result. As I said, I would like to emphasize this result, which is basically, it is an extremely cool star. So it's extremely difficult, according to what we, the way we were doing the analysis in exoplanet science, the way we were deriving the velocities from high spectra. So the studies is very cool. It's less than 10% the mass of the Sun, and the planets are pretty close to the star, but still within the habitable zone because the star is that cool. And they are both are within the habitable zone, and they are very close to the Earth in terms of what this index. It is Earth similarity index. The planets have many properties that we can infer from the mass that they have that are very similar to the Earth. And this year, this was published by Maria's science in 2019, and this year we have another publication in the Carmenes team that they get another planet below the map of the Earth. This is already a significant result, and is 26 days, which is farther away from the, on the outer part of the hydrogen. Apart from being involved in carbons, I have been involved because my time is very limited because I'm involved in many projects. I have not been too much involved in carbons as much as I would like. I would have liked it. I have been involved in the Hades. We started Hades before carbons was on Sky. Hades was a collaboration. It was a paper by one of my PhD students, Toledo Padrón. Was the base of a very small planet in a very short orbit. So in this project, when we were executing at the Hard North at the TNG in La Palma, we were discovering many exoplanets. I would like to highlight these two. I already mentioned this one of my PhD student, and also at the time Alejandro was my PhD student at the IAC. He also discovered this planet. I was commenting in the cafe before coming here with David. This planet was very difficult to detect. This star was one of the lowest activity stars in the sample of AS, but we were persisting on observing this star until we reach this planet, which is here is close to the inner part of the hydrogen. I would like to highlight also here that we have been realizing the data of this star to 3998 this year with our new PhD student, Atanas Stefano, and we have detected another planet, planet B, which is in the hydrogen. So, we are living in the era of space missions, and these space missions are from TESS. It was launched after Kepler. We are in the era of characterizing the closest exoplanets and detecting new ones, and detecting Earth-like planets in the habitable zone, and planets in close stars, in nearby stars, that we are able to do future analysis in the near future. And for instance, the Kepler field was ideal to have statistics, but the stars are typically very faint to be analyzed further. So that's why TESS missions and also CHEOPS are now focusing on the closest stars. Then ESPRESSO is now having very impact papers every week on trying to get the atmosphere of or transits of or measure temperatures of planets. And Plato will be is the next mission that will be will be trying to get the Earth twin, trying to get the transit of Earth-like planet orbiting a solar-like star. This is very challenging, but we will see. I mean, the current the current prediction from the launch of Plato is at the end of 2026, and it seems to be fixed, and there's no problem to reach it at that time. So let's see what happens. In any case, these missions are only, we can only start the information from the mission only if we are able to convert with ground-based instrumentation. And typically ground-based high resolution ultra-stable spectrograph, like expressive targets, NESS, which is a NESS working with HARPS, and HARPS North, HARPS 3, and Hernández are European. As I have said, we will concentrate efforts on trying to check for X-light habitation nearby stars in Leleu. So this is the current instrumentation related to high resolution spectroscopy, ultra-stable spectroscopy, that the ISC has been and is participating. Well, I was not, I am participating in cabinet, but I was not coordinating anything. I was coordinating the interfaces of ESPRESSO, and I am coordinating the instrumentation efforts of the ISC of news, actually. We are helping Chinese in Chorus, and also Andes for the AUD. Okay, NIRS. NIRS is a near infrared high resolution spectrograph, which is what's initiating regular operations in April last year, in 2023. It is able to reach around 70,000 in resolution. It has two modes, high accuracy and high efficiency. I highlight here the fiber link because this was the part that the IEC was contributing. I don't want to enter in details, but these are the real picture of the different subsystems of NIRS. So from end, fiber double scramble, and then this is the back end, and the spectrograph. This is the whole NIRS instrument mount in La Silla, and the 3.6 meter telescope. This is the front end, just of the Capricorn focus, and this is the enclosure of the system, of the instrument. The instrument is performing very well. I would like you to stay tuned because in the next months we will be publishing many papers from NIRS, and we will be entering. We will be demonstrating that the near infrared could be also used for being below the meter per second level. This is an example that has been published by Clément Thibault, which is our colleague from Canada, Montreal. This is the Proxima Centauri radial velocities of NIRS, and this is the model of the two models that have been discovered by the ESPRESSO consortium. As you can see, the velocity of NIRS can reasonably well follow this model. We are doing now a better. I mean, this is just a guess. I mean, this is just an exercise. We are doing the right modeling with the data we have taken this year, and we will be publishing the results soon. HAR3 is a different concept. This is an instrument that will be installed at the INT in La Palma. It is the HAR3 consortium is a consortium of almost 10 institutions distributed in UK, Sweden, Switzerland, and Canary Islands. So in Spain, it's represented by the IEC. The IEC in this project is taking care of the thermal enclosure of the instrument. And the project, the Perhampton experiments, is led by the Nobel Prize students. We expect to be at the telescope next year, hopefully, by summer. Let's see if it's possible. And what we are happy doing is to convert the telescope into robotic, so we will run robotic observations. So without supervision, let's see, we will see if it works. It seems that it's going well. The project will be changing the way we are addressing the search of Earth-like planets solar stars. We will be doing almost continuous observations, more than 100 radars per year, and we will try to the goal of the project is to find an Earth twin, so an Earth-like planet orbiting the solar star using radar velocities. So it's similar and in a nearby star, similar as the Plato goal, but using radar velocities. It's a challenging project, but we think that we are able to do it. CHEOPS is a project which is an instrument similar to ESPRESSO. The visible is going from 42,000 angstrom to 4,200 angstrom to 7,800 angstrom. So similar to the ESPRESSO wavelength coverage. And we will have also another UV instrument going from the atmosphere cutoff the wavelength of the field of the visible. So the work will be similar to those of ESPRESSO, so it's like planets, we have those nearby stars, and now the person we hope that we have the first line in 2028. This is very optimistic, but we are pushing. We have a meeting next week in China with the Chinese colleagues, and let's see how if we are able to fulfill this conference. The PIC Andes is another instrument where we are participating. The AIC, we are leading the Spanish contribution to Andes. And also the IAA, so it's the Astro-seminar Andalusia and the Centro de Astrografía, they are also participating in the instrument, in the Spanish contribution. And this is also a challenging project. It will be the goal is to have from the ultraviolet to the K band. So we'll have 4 arms. So the K spectrograph, the UV spectrograph, and these two will be in the nasty B platform of the ELT, and then in the cooler room we'll have the RSA and the YSH spectrograph. So we will be able to try to understand the atmospheres of Earth-like planets, particularly using transmission spectroscopy. With Andes, and it will be interesting in dealing with Andes in go further and trying to get signatures of life. So we'll be able to measure and to detect atmospheric transition of molecules that are considered biomarkers, and we'll be able to do this in planets. Using the technique of transmission and also in reflection. And reflection is really an important step we are now pushing, because the reflection is, this is a typical case we will have in the solar neighborhood. You know that only 1% of the stars, of the planets in the solar neighborhood transit. So if we are able to detect those planets in the Handwave zone, we will be able to observe those with Andes. So with Andes, we will be able to detect, for instance, Proxima in a few nights with high accuracy or high precision, and we will be able to detect also oxygen. So this is really an important project. This year, there have been, last year, there was a white paper led by Pepe, who is coordinating the working package in Hernández related to atmospheres of exoplanets. And he was, in that paper, there is the different molecules that we are able to detect and the nights that we need to get to that level of detection. So the project is very interesting, very challenging, because this is really a big collaboration of 13 countries and more than 35 institutions. So it's a really challenging project, but the project is going quite well, and we are ending the second phase, the PDR, by next year, summer next year. This is the transit of Mercury on the Sun in November 2019. I would like to just show this because this is a good representation of what we will be doing when, instead of trying to model an Earth-like planet around an N-Dwarf in a close orbit, we will try to do something. How we are trying to get the atmosphere of an Earth-like planet orbiting a solar-like star. This will be how we will solve. This is I took this example from a person that was doing a talk in another conference in exoplanets, and he was from a live collaboration, so live mission, and he was showing this as an example of how difficult it would be for us to do this. Indeed, 1,000, 10,000 photons that cross the atmosphere, 1 over 1,000 or 10,000 photons cross the atmosphere of a Jupiter planet. In the case of a large planet, it would be 1 over 100,000 or 1 million. So this shows the difficulty of how difficult it would be to solve this when we detect an Earth-like planet, how difficult it would be to get the information of the atmosphere and to be able to say if the planet, if there are these components in the atmosphere that allow us to claim that there is the possibility of life. So this is the path of the NASA and ESA, of the missions that are now being currently and the number that being predicted to happen. So Plato in 2026, Ariel 2029, and then these two missions that are now being discussed and maybe will be in the 30s or in the 40s. With this type of mission, we may be able to do the characterization of an Earth-like planet or the habitable form of a solar-like star. And we will also need the ELTs telescopes from the ground. This is how the ELT looks like in 2023 in summer. Now it's a little bit more advanced, but still. And with the ELT, with Hernández, we will be able to not only answer to this question of if a planet out there has signatures of life, but also we will try to solve to do the Sanders test, which is trying to measure the acceleration of the universe in real time. And this is how it looked like the signature of that measurement for in quasars and relatively larger than 2. We'll see that this signature is about a centimeter per year. So we'll have to have a very precise instrument to really reach this goal. We'll need this kind of instruments, the laser frequency cone that we were testing at the beginning of the last decade. We were collaborating at IC with the Menlo system company and also with the Max Planck quantum optics in Germany. So the laser frequency cone is the instrument that is locked to an atomic clock. So it is a very precise instrument, and this is an instrument that is able to calibrate the spectrograph that we are designing, and it would produce a long-term stable calibration. And this is needed for projects like HART3, because this project that is a long-term project for 10 years, and also for Andes in particular, because in this case we need to have a long-term, we need to be by decades of solving this kind of equation to really detect this very small signature. And we need a real, extremely good calibration system. The only one we can see is the laser frequency cone. However, we were doing this kind of works in 2020, we published this in Nature Astronomy. We were able to demonstrate that in short term, laser frequency cone is reaching the 1 centimeter per second precision. But what we haven't been able to demonstrate is the long term. And it's because there are many things that are failing in this system, and there are other concepts that are being proposed for other instruments. In particular, we have a different proposal for laser frequency cone for NIRS and also for HART3. So all of them, I mean, nowadays in the world there is no instrument called laser frequency cone that is able to demonstrate long-term stability. But we will see if in the near future we are able to demonstrate that. We will need it. This is ESPRESSO. It's a video to show how ESPRESSO was built. This video was done when we were in PBR. So it's showing that ESPRESSO is it's like a super hard. It's an extremely high resolution spectrograph. It's a spectrograph can work with either 1 UT or the 4 UT of the BLT. The light is coming from the sky, and this is going, what we call the Kepler train, is going through a few optical elements and going down to the Kepler room. The Kepler room is, well, this is, as I said, coming from the different, it could come just from one telescope or all of them at the same time, or several of them at the same time. In the front end, which is here, we receive the light and we are able to combine the light if needed. And what we are able to do as well is to inject the light into the science fiber. As in many ultrastable spectra, we have typically two fibers. One is a fiber that is used for the science target, and the other fiber is used for either for calibration or for SCAR. What we have here is there are several things that happen while I was talking. We picked up the pupil stabilization camera and also the image stabilization camera, which we are trying to keep the star always in the center of the fiber, because moving the star, if you allow to move the star in the center of the fiber, you create grand velocity variations that are not desired. This is the tubing system that is able to change, because the spectra have different modes. You have a high resolution mode at 140,000 resolution. It has the multi MR mode, which is the mode that is working with all the telescope at the same time at 7,000 resolution, and the mode that is working with the high resolution close to 200,000 resolution. This is the optical lens, the optical wedge, and the two cameras from the blue and the red. This is the vacuum vessel, which is allowing that there is no change in pressure in the instrument, and then the enclosures, the thermal enclosures, there are 3 layers that allow us to really keep the temperature stable. Okay, so I think, yeah, this is what I have said. In the ISC, we were doing mostly many things, the optical elements, the fiber link, and the optical elements are mounts. This is me in 2016, 2015, with the instrument. And this was the first slide in November 2017. This is the Kepler format. As we are in a big telescope, we have a very wide beam coming from the telescope. So the pupil, what we do is to break the pupil into two. So we are creating two slices in the image of the spectra. So the three modes, the ultra high, the high resolution, the ultra high resolution, and the multi-MR mode. So we are, as I said, this is science fiber, so both are science fiber. We are breaking the pupil, so this allows us to reduce the size of the whole instrument. And then this is the science, the fiber beam. So this is the two slices of the fiber beam. So it's somehow more complex than HARPS. This was needed because otherwise the instrument would be the main collimator, so the main optical element, once the light entering the spectra, would be huge. This is to me this picture shows how precise is ESPRESSO, just because the quality of the points there. This is a real spectrum, and these are the Fabricano lights. This is the temperature stability overnight, quite stable, and the dependent precision. This is the extremely high resolution, ultra high resolution spectrum of the oxygen of the atmosphere. This is the stability during one night, which is at the level of the few centimeters per second. This is what we have done in ESPRESSO in the GTO that has just finished. So we have been distributing the time in groups that are related to the surface, like I thought, of and Barros, the atmospheres of exoplanets, and then the mass and density measurements of transiting planets. Then we have been also looking at the variability of Mercosa by certain quasars, and also we have done some other science of stimulating the quasars. These are just a few, just a few results from ESPRESSO. It was one of the first results from my PhD student. It was the detection of extremely high density target, which is this one, close to the pure iron model, one of the highest measurement on exoplanet. This is the beautiful resonant system of 6 planets. The target POI 178, which shows the incredible good synergy between the space missions and ESPRESSO. Here you can see the detection of scales, and here you can see the velocity of ESPRESSO of all of them. Then another example is the detection of a low mass exoplanet in transit. And also in the velocity. This is the L9859 target, and the planet has almost half of the mass of Venus. Here. Quite interesting, and it's extremely precise measurement from ESPRESSO. This is an example where we were able to calculate the 5 with the TESS, and also with ESPRESSO, we were able to find the velocity of this target. For this start, for HT23472, we were able to discover several super Earth, and also what we call 2 super Mercuries, which are located here, at extremely low mass. So it's extremely difficult target that only ESPRESSO can resolve. So now we are approaching Barnard. This is the proximal result of ESPRESSO. This was a candidate super Earth done by Mario Damaso, published in 2020. Still to be confirmed. This is the incredible performance of ESPRESSO. So here we can see the detection. This is a paper led by Alejandro, my postdoc at ISC, Alejandro. And this is the incredible velocity of Proxima B, and the detection, hints of the detection of the Proxima B. And if you compare this with the previous detection by Leleu in 2016, you can see how good this is ESPRESSO. So this is the velocity curve of Proxima. I tried to do a zoom just to make the velocity curve more or less the same size, but really you can see the scatter of the point here, and you can see how ESPRESSO is really describing very well this curve. This second planet was done in a new, after several years of observations. The good thing is of ESPRESSO, or another thing of ESPRESSO, is that the stability of the system is such that indicators like the Fulmingham maximum of the interconnection function is really stable and allow us to really define very well the activity of the star. So you can see how good the GP is following the Fulmingham maximum here. And we are doing at the same time we are combining the Fulmingham maximum to the velocity. We are analyzing both things at the same time to really be able to model the velocity and keeping the activity under control. And this is shown here. And you see the result. The largeness of the is around 27 centimeters, and here the largeness of the focal mass is 60 centimeters. This is a promising performance. So this is the final result. This is after several years after the paper by Alejandro, Joao Faria from Portugal, and also we were following that paper. We were seeing that we were really great characterizing the proximal planet, and with ESPRESSO we are really, this is at Falco 1D, so it is inner regions of the Hydrogen, but still this is a planet with almost twice the mass of Mars. So this is amazing. And in ESPRESSO we are giving the error of the velocity since this is something to me is very surprising if I am been working with ESPRESSO. You see here the size of the accelerated of the second planet. This is another set that I mentioned at the beginning. These two planets. To be honest, here this is Carameles and this is ESPRESSO. Carameles was used for the baseline of the to get the characterize the data of the and then the model, 3D model as well. But the ESPRESSO is really making the difference here. And these are two planets that have the mass close to the Earth mass, and they are well described. Amazingly described with the ESPRESSO points, and also Carameles is well problem. So as I said, the two planets are close to the Earth's mass, and they are within the Hamilton. This is another more recent result. Also, Alejandro is looking at the transit of the POI 238, and we find the perfectly balanced velocity curve of both planets that are located. In particular, we are here trying to see, trying to understand this dichotomy of water walls and rocky planets. And here we are showing that this that was done by Rafael Luque and Rick Payet in Endworks when you put the K-words. It seems to show the two peaks, but still there is not statistic enough to really show the same picture. This is the whole contribution to ESPRESSO, the green points. As you can see, with ESPRESSO we are filling this region where there were no other instruments before. And now I'm going to proceed to Barnard, sorry. So I started with this candidate planet that was published in Nature in 2018. That was later challenged by Jack Lubin in 2021, and Diego Ortigo in 2023, and I had to challenge myself that planet using the ESPRESSO. If I go back to 2019, in the PhD student we were collaborating with the Carameles team to really do the activity of this star. We were doing a paper where we were able to measure the rotation period at about 45 days, and we were able to measure the long-term cycle of 10 plus 4 years, particular from calculation K, but in particular from assess methodology. So if you go to ESPRESSO is since we are jumping in one order of magnitude in velocity precision, we start to see clearly what is what. And here, if you can see, this is the formula maximum, as I was telling you before, regarding proximal in Barnard is the same situation. It's really well modeled, and we were doing again multidimensional GP with harmonic oscillator at P and P divided by 2. And the reason is that in the Fourier maximum we are in this red periodogram, we are seeing that most of the peaks are at periods larger than 100 days, whereas for the radial velocities we are seeing that the peaks, the period, there is a significant contribution to the peaks in half of the rotation period. So we were considering this to do the global model with at the rotation of the half of the rotation to allow the velocities to also solve the activity. In particular, what we are seeing here is that these peaks are really half of the rotation period, and all are all related to activity. At the beginning of the project, I tried to do many models by trying to put a prior on the possible planet around this peak to be able to, if this survives the model, including the activity model. I never get the result. At the end of the project, I tried again, and I never get. I was doing thousands of modeling in the last 2 years. And what we are seeing clearly here is that this number of variations are peak to peak are like 8 meters per second. We are clearly showing the activity of the star. So we have to subtract that. But we can do it because we have the activity model well consolidated. With that, we have maximum simultaneity because expression is very stable. Stable. So when you are doing that, and this is the most simple model, only with the GP, you see that after you subtract that, you find a peak here at 3.15. And several other peaks that I think they are also signals of additional planets, but I couldn't confirm. So this is the research I was trying to do with trying to give. We can recover this ESPRESSO, given that the precision is extremely high. We can recover the planet, the candidate, super Earth. And I wasn't able to do it by using Y prior, uniform prior on period. I get a semi-amplitude at around 0.4, significantly lower than the published value at 1.2, 1.3 meters per second, and it was going to zero. So this is indicating that there is no, the signal is not there. At least the signal that we found is in 2018. Then if I give some freedom there, there is this always is going even further there. If I keep the prior on a small region around 233, again I get the very small semi-amplitude, which is consistent with zero. And then if I simulate the injection of a signature, of a planet signature at this 1.2 meters per second at the period of 233, and then I run the model. I mean, I inject this signal on the activity model that I get from ESPRESSO, from the analysis of ESPRESSO data, and then I reanalyze this data by injecting this signal. And then what I get is really a clear detection. So I am pretty convinced that I don't have the plot here, but if you add this signal to the velocity, you see almost by eye, with ESPRESSO, you see almost by eye this the signature of possible planets. So in conclusion, ESPRESSO doesn't support the system of the 233. So if we are trying to evaluate the signal of the 3.15 base, we see that the signal is going down. In fact, and so in false alarm probability, this gives us an indication of how significant is the signal, and we are increasing the number of points of ESPRESSO data. After 110, we reach the level of where we always say that the candidate is quite significant. And as you can see, we are doing this model always by using a GP, so the same as I was showing before, and you see that the precision in the period is getting better. I was testing this with all the different analysis that we are able to do with the velocities. So using the Kepler matching, what we got from the data reduction software of ESPRESSO, which is quite good as well. I'm also using the line-by-line software from Toledo Padrón. This is the whole amount of data we were using in ESPRESSO. Clearly, by eye here, at least when I was looking at this data and having the result that we were getting previously, what I thought I was seeing here was the activity related to the cycle. So I decided to add another model before injecting the GP, which is doing adding a double sinusoidal model to model the long-term activity. So in this case, what we are doing is just, so in this complex model, we are having the long-term activity, then the GP, and then, of course, the planet. And you can see that the planet is peaking here very strongly. It's extremely high in fact. It's a high, low fact, still over the 0.1% fact. And then when you subtract this 3.15 planet, you get here another candidate at 4.5. This is the analysis was done. The analysis was done with only ESPRESSO data, and then only ESPRESSO plus Harsh and Harsh North, and then only ESPRESSO plus Harsh North and Hernández. This is only here the result with the Hernández. So we were able to, with wide priors, uniform priors, we were able to get the cycle at the 8.8 years, and with a baseline of 8 years, which was the whole period from Hernández to ESPRESSO, and then 140 days for the rotation period. Very well defined. This is the analysis of ESPRESSO only. Why ESPRESSO only? Because even if you are adding data, the data you are adding has less precision, so sometimes it's worsening the results in the posterior distribution of the parameters many times. So ideally, what we need to do is to continue with ESPRESSO. As I said, this is the activity model. The cycle is in red, then the GP is in gray, and this is it looks like a band, but in fact it's just the 3.15 days going up and down. So this is the result of ESPRESSO only. What we get is a planet with this semi-amplitude of 15 plus minus 7 centimeters per second. Again, we are doing the DL centimeters per second. The mass of the planet is a few times the mass of Mars. The eccentricity is, even if we leave as a prior free the eccentricity, it is going to lower values, so meaning it is circular. But the planet, as it is 3.15 days from the star, is quite close. It is quite hotter than the Earth. This is obtained with a wide uniform logarithmic prior from 0 to 50 days. So we are giving this wide range of days as a prior, and the delta, the increasing variation evidence is quite significant. So this is the location of Proxima B, of course, Proxima B, and this is the location of Barnard. Then, again, if you can see here, the RMS of before was 60 centimeters per second, and after is 45 centimeters per second. The RMS of the full Wiham maximum is about 30 centimeters per second. So this was, to me, and it seems that there is a lot of scatter here. Still, you can see the relativity curve, but there is somehow significant scatter. And I think this is related to the fact that there are more signals that we are not modeling. And when you do the modeling, you see how good is the relativity of the main planet. So this is not confirmed in the sense that the Bayesian evidence doesn't give you a statistical confirmation of that this system, this candidate planetary system is there, but we are expected to confirm that in the near future. But the first analysis, when I am doing, this is the the whole analysis, including the 4 planets at the same time, plus the whole activity model, and so on, but using small priors on the orbital periods of each of the signals. In any case, you are seeing that once you shoot each signal, the other appear quite significantly, and even the smallest planets will be taking 20 centimeters in diameter. This is amazing, and will be counted with 0.72. So Earth masses, or just less than half, less than double the mass of Mars. Even though this candidate planetary system will be inner to the habitable zone of the star, but this is indicating somehow that the analysis indicates somehow that most of the stars, once you have the capability to explore them, and once you have the precision to explore them, you can show that there are planets out there. Most of them. If we were not able to find planets in the nearby stars, it was because we were not having the capabilities to do it. So we are not giving up with Proxima to find another planet in the outer layers, outer parts of the habitable zone, and I am not giving up to find even a planet in the habitable zone of Barnard. After, if we are able to confirm the whole system, we will continue, because it may be that there are smaller planets there that we are not seeing because it is the synergy is very weak. So this is what I did, and as I said, this model is not from the Bayesian point of view. It's a similar model to just one single planet, but as you can see, by giving priors that are quite large, we are retrieving the semi-amplitudes. This will be how it look like it would look like the location of the four Barnard planets. So by including the additional planets, we reduce the strength of the variable semi-amplitude of the primary planet. And there will be 2 singular planets with this, with the masses almost 3 times the mass of Mars, and then even smaller planets. At the time we were publishing the paper, or during the process of publishing and then waiting for the first release to be released. We realized that the TESS, we were checking this from time to time, but we realized that TESS was associating the Barnard star in July 2024. So we were in the process there of the referring process, and the data was made public at the end of August 2024, when the paper was already accepted. So we were there, we took the data, and we prepared quickly a new publication, which is led by our student, and we are seeing that we don't see the transit. So this is the black points are the line curve of TESS after the trend, and this is the expected transit, and we are not seeing anything. That's all. This was my talk. Too long, but
Thank you, Jonay. We have time for questions.
Thank you very much for your talk. You have given us a lot of information, difficult to digest for a lot.
yeah.
One question, well, I have several questions, but just one, two. How do you select the candidates to be observed with ESPRESSO, you or the collaborations? I mean, are they previously detected planets? Are you looking for new one planet?
From the beginning in ESPRESSO, we were considering that ESPRESSO was going to be a step forward. So by definition, we were observing all the nearby stars. at the beginning the plan was to do the JK endorse. All the main targets in other.
What you make example of
well, yes, but the point was, to be, to do the closest, the nearby stars. Of course, depending on where are the spectrograph, by keeping in mind G, K, and M dwarfs, low activity, and the fact is that we were only succeeding in the endorse because of the reason I was made at the beginning of the talk. Because we are trying to look for closer regions to the star, because we can have an orbit in less than 30 days. This was for instance, for Barnard, the habitable zone is in between 10 and 40 days. So we were, the goal of ESPRESSO was to explore the habitable zone of all these stars. We realized that K dwarfs and G dwarfs requires long-term, extremely long-term programs. You cannot solve this. And in the concept of how the DLT works, it's not that easy, particularly for G and K. So that's why we are also, in particular, we I mean the IAC, and we are also in the same group, and there are the people from Geneva. We are doing this HART3 project because this will be concentrating and focusing in the stars for a long term. So observing the stars every night during 10 years. This is what we have to do if we want to find an Earth-like planet around G-type star or K. Because the periods we are talking about from 100 or more than 100 to 300 days. This is very complicated. And you need to, if you get the signal, you need to repeat the signals every year. So you need to get data from many years. That's why at the end of the ESPRESSO GTO, where the GTO lasts for about 4 to 5 years, and we were doing many things at the same time, like typically happens in this kind of projects, because there's people interested in different things. We were dividing the time that we worked, and we're about 280 nights of PhD, which is a lot. But we were dedicating 80 nights to the program that was working group 1, which is related to blind searches of exoplanets. And then there are another 80 nights that were dedicated to characterization of transit planets. So we we were trying to do this, and we were selecting the stars that are, but then the problem of, as I said, in indoors, the activities is more dominated with by the spots, and you can see departures. I mean, if the activity seems to be quite intense, you see the departures that you are seeing can be modeled quite nicely, and depending if you are trying to find a planet which has a period longer or shorter of the rotation, then it will complicate the things. But what happened with the K dwarfs, you will be always trying to find a planet longer periods than the rotation period, which is typically the rotation in between 25 or 20 and 40 days. So if you want to see the habitable zone, you have to, but we have to well sample the rotation period, and then trying to see if there are these very weak signals, and then you have another problems related to convection and oscillations and small details that you at this level of that the accuracy you need start to complicate things.
And then, given your result in Barnard star, you prove that the previous detection was a spurious detection due to activity and so on. What is your feeling about in this case is a unique case or not? I mean, what percentage of already reported planets around active stars are false detection?
It doesn't have to be an active star. I mean, with my feeling was that we were pushing the limits of the instrument that we had at that time. Now, from the time it was in the paper, so we were seeing that we had to add. At the beginning, we were realizing that only with camera we could not get it. It was something we were saying, okay, it may be that Carmenes is at the limit of the precision to get, because Carmenes is about precision between 1.5 meters per second, and this planet was at 1.2. So it was, at the limit. Maybe because it was a very long period planet, again, it's difficult because you really have to get replication of the orbit several times. So 230 is almost a year. So you have to get, if you had, at the beginning when we were publishing that, we had 2 years of carbon data. So we were saying, well, we need to add more instruments. We were adding instruments until we start to see that there is a peak in the signal. Yeah, what Jonay did was to truncate so he was extracting, removing part of the data and see what happened. He was doing this until he realized that if you remove part of the data, the signal disappeared. And this is a delicate thing. So all the instruments that we were using, well, there were some data from HARPS that wasn't the most important data. All the instruments we were using were on the limit. We were using a lot of HIRES have a precision of 3 meters per second. So we were pushing to the limits. Then the activity. The activity is the key point here, because in the previous instruments we were not clearly seeing the activity in the velocity. We were not, because we knew that the Barnard was a very long period. It's difficult to evaluate. We were doing the activity using the activity indicators. This was our part of the contribution with the PhD student, and we realized that the rotation period was at the 140. By chance, the 1 year alias of that is 235, 240 days, very close to the signature of that planet, of that candidate. So this happens. I mean, there are other. If we are, and nowadays, now we are using multidimensional GPs, which avoid the overfitting of activity. At that time, we were not so used to do that. There were not the tools to do that. And also, then, as I said, it's always easier to try, if you have the activity, to try to get things inside the rotation period. So shorter periods than the rotation period. Longer periods of the rotation period are difficult. But in the case of ESPRESSO, since we are doing this analysis with the multi-GP using the Fourier maximum and the Hernández at the same time, we are pretty sure that we are not overfitting. So we are pretty sure if we model a signal outside the longer periods of the rotation period, we are not removing part of the signal because we are modeling also the activity. And this is because ESPRESSO is a very precise system. But I mean, this has happened. There are many more targets in the field that are being reanalyzed, and we realize that there are some false positive that we are detecting. But this is science. I don't see any problem with detection that we were almost. Well, we call it candidate. We never went to a catalog of exoplanets.
Yeah, because I think you criticize it.
No. But the point is that it was. I was really because I was in the ESPRESSO consortium. I was in the beginning trying to demonstrate that the planet was there. I couldn't.
Thank you.
Any other question, David?
If I understand well, the no support of the previous planet detection is related with the activity in similar analysis from the rotational field. But you also mentioned activity cycles. This is model good enough to see the cycle also is related to the planet previous pattern.
No, I don't think there is a connection between the activity of the cycle and the planet. The cycle is quite long. It's, as I said, it's almost 9 years, right? So, so the cycle is changing. It's like fitting. Is slightly changing the velocity of espresso. This is what we think or what we propose, and we are somehow this signature that we are seeing in espresso. We are not able to see it in high strength. Maybe because there is this double sinusoidal. The amplitude can be reduced at given times, or maybe también because of the jitter of the other instrument, the previous instrument. So with the quality of the data, well, this is the Fulcrum maximum, but the quality of the data we had before is not good enough to really see signature at this level. You can see. Maybe it was the.
Just click the.
No, I think this is because of the Zoom. Well, we were almost at the end of the talk, so it was funny. I think as I said, the cycle is quite long to be affecting but the rotation could be affecting this signal. The test, the fact that this is so close to the 1 year alias was a warning. We were discussing this in the paper of Borja in 2019 because there was a question from the referee saying, you know that the 1 year alias is close to the planet, the candidate planet that you were planning last year, and we said, yeah, okay, but it's not the same period, it's not the same frequency, not exactly the same, but quite close. We were believing that the signal was real, but now I don't think so.
And do you think more observations could be help to figure out finally this planet, or perhaps not?
Yeah, probably yes, but I didn't have the time to show it, or I didn't have the plots to show here. But if you, as I said, if there is any signal, it will be a different planet than what we were publishing, because espresso is the quality of espresso is such that we will, a signal with more than 1 meter per second will be clearly seen. I didn't have the plot here, but as I said, if you inject a signal like this in the data, in the velocity data, that you are seeing clearly the changes due to activity, you will see, on top of that, you will see by eye, and being a long period planet, you will see by eye how the velocities are going up and down because of this a priori large planet. So to me, this is quite clear.
Any other question? Any question online? But I have a curiosity. You mentioned before that the synergy between ground-based and space telescope is very important to detect planets. And I was wondering what is the best combination used so far, and what would be the best combination using the forthcoming instruments?
Well, in the near future, up to now, I would say that the best synergy is with ESPRESSO, and ESPRESSO have been there. TESS is a mission that is going, having for 30 days every field. So if they are able to detect something, it may be that it is not at well, of course they have good detections, but for instance, CHEOPS is going back to those fields once you have detected to really confirm planets, and the combination of CHEOPS, TESS, and ESPRESSO is ideal. And then in the future, there is this Plato. Plato would be a challenge, and I mean, Isai is putting a lot of effort on that, and we have to really, I mean, the whole European community have to make Plato successful some way. So there is a group that is being organized for many years to now to be able to follow all the fields, all the stars in Plato with high resolution, hundreds of nights. At all the facilities in the north and in the south, in particular, especially, there is an agreement with ISO to really dedicate a lot of nights once Plato is on the sky, because if there is a detection, and if there is just single detected Earth-like planet orbiting a solar-like star, all the mission, this will be just the good starting point for missions like LIFE or Habitable Observatory, because they are a significant investment and they are planning somehow, but there is not really the compromise to do it, and this is for 2040s. But having these kind of detections will for sure explode the field in the sense that if there is one, there could be many, and of course we know that there are many. The problem of detecting them is a challenge, but by detecting one, we will be able to. I mean, we will have the excuse to really push our governments to invest in this.
Nice. Thank you very much. Well, if there are no more questions, let's thank the speaker again. And thank you very much for joining. Bye-bye. Que está bien, al final. Sí, ¿no?
Sí,